everyone. My name is Václav Miklas, and I'm one of the consulting engineers at the European Brine Research and Engineering Office. And I would like to thank you for joining us today. I really appreciate you taking the time and being interested in today's topic, which is modeling techniques for packed column. So what exactly are we going to cover today? If we take a look at the agenda, it's not going to be just packed columns, but we will start from something more general. In the first part, I will explain the difference between the ideal stage model and mass and heat transfer model, which are two different calculation approaches we have in Promax when it comes to distillation columns. In the second part, we will get from something more conceptual into something more practical. So what might be very important for you as a user is to know what kind of inputs you need for the two model types. So that's what we will be discussing in the part B. And in the last part, we will be talking about the main thing or main topic of today. So packed columns using the mass and heat transfer model. We'll probably spend around half of the webinar on this crucial topic. So let's start with the comparison of the two model types. If we take a look at these two pictures, on the left-hand side, we have the kind of idea behind the ideal stage model. So this might bring some memories from university, where we were working with something like make-up field diagram, and basically for a simple, binary mixture, all you care is equilibrium, and all you take into account in terms of operation is your feed composition and your reflux ratio, which basically give you these operating lines. And you have some desired purity of your bottoms and distillate, and you can come up with how many ideal stages, so how many of these steps you would need for this mixture. In Promax, of course, we can model more than just binary mixtures. We can model mixtures with tens or hundreds of components, but the main idea is the same. So we basically assume that on each of these theoretical trays, you reach thermal equilibrium. So the temperature of vapor and liquid phase is going to be the same. And also we are going to reach chemical equilibrium. So that means that if you would let vapor and liquid sit for a little while, nothing would change anymore in terms of composition. And that's not really what's happening in reality. We would be really happy to have these perfect trays, but in reality, we have some efficiency to take into account, or some other kind of conversion factor, how we can turn this concept of ideal stage into the real column. The second approach we might use, and we have incorporated into Promax, is the mass and heat transfer model. So we don't live in matrix. We kind of have to think about reality and what is possible with the internals that we have available. And for a tray column, for instance, you can imagine that the vapor and liquid mixture, it doesn't spend unlimited time on a tray, and we have limited interfacial area. And so it would be, of course, and it is beneficial for us to investigate what exactly is happening on the tray and be able to quantify the mass transfer rates as well as heat transfer rates from one phase to the other. We can be thankful as process engineers that there are some correlations that allow us to do such thing. So we are actually able, knowing physical properties, knowing the interfacial area, we are able to quantify what's actually going on in terms of concentration change in each of the phases, and we are able to basically get something that reflects reality way better than the ideal stage model. One thing that I should note, that this is a non-equilibrium model, so we end up with non-equilibrium composition and also with different temperatures for each phase. This is going to be evident from the next slide, where we will take a closer look to what's going on the phase interface. So this might represent an absorption of some component A from vapor to liquid. We have vapor on the left side and liquid on the right side. And what's happening is that we have some initial concentration of this component A. And if we allow the mixture to be in contact for some time, the composition is of course going to change. And if we let it sit for a really long time, we would eventually reach equilibrium, which is represented by this gray, by these gray lines. This is what we assume for the ideal stage model. In reality, since we don't have unlimited amount of time, what is happening is that equilibrium is only at the interface, and then we have some concentration gradient towards bulk composition. And with mass and heat transfer model, we are able to reflect this real nature of mass transfer in distillation columns. The same applies for the temperatures. For the ideal stage model, this would be just one line because the temperatures are equal to each other. If we're using the mass and heat transfer approach, we would have some, bulk temperature and then some temperature gradient towards the temperature at the interface. And on the opposite side, it's going to be the same idea. This was just to explain the main difference between the two models. And now we're going to discuss what it means to you as a user in terms of the required inputs for the model. So if we take a look at this slide, this shows you the parameters that are necessary for both the ideal stage model and mass and heat transfer model. So regardless of the model type, you always have to put these in. First of all, of course, that's quite straightforward. You need to select which one of those you want to use, and you also have to select column type. Column type in most of the applications is just general ideal stage or general mass and heat transfer, but we also have some specialty types that I will introduce to you in a bit. Second parameter is number of stages. And as you can see, this really has or might have very different meaning for different model types. So for ideal stage model type, we don't really distinguish between the two. We have, these theoretical trays, these equilibrium trays. In terms of the decision, if it's straight column or packed column, that depends on what sort of kind of conversion factor we're using when translating this into reality. So if we are talking about straight column, that would be overall efficiency. If we are talking about packed columns, that would be height equivalent to a theoretical plate. And you can basically take these coefficients into account and translate it into what depth of packing you need or how many trays it represents. For the mass and heat transfer model, we do distinguish between straight and packed columns. For straight columns, it's very simple. You just use the number of trays that you would have in reality. So if you want to model a 20 tray column, you simply use 20 model trays as well. For packed columns, each stage represents a calculational increment. And we'll discuss this in the last part in depth, so I'm not going to touch on this too much anymore. But this is kind of just to give you an idea about what does stage mean for different model types. Another two things that we have to specify for any model type is pressure profile. So this is something that you can directly specify as a user, or you can let Promax calculate it if you also put in geometry. And last but not least, specifications. This has to correspond, the number of specifications has to correspond to number of degrees of freedom. And so basically anytime when you have a reboiler attached to a column, when you have a condenser, or when you have a side cooler, this gives you a degree of freedom. And in order to have a solvable mathematical problem, you have to provide Promax with a specification in order to be able to solve the column. So these four things are something you have to put in Promax whenever you're modeling a distillation column, regardless the model type. Where we see the difference is in geometry. So here we have rows are basically the model types, and columns are the type of application. And here in the table you can see the column types. And as I said, we do have some specialty model types, the T-suite ones, which we use for amine sweetening applications, but also for some other applications such as sour water stripping, etc. What you can see here is that for the ideal stage model, you actually, in most of the cases, don't have to specify geometry. The only exception is amine absorbers. The reason is that for amine absorbers, what's really important are kinetics. And what plays an important role in kinetics, of course, is the quantity of time. And you cannot really find out how much time you have for the reactions to happen if you don't provide Promax with that information about geometry. So that's the reason why in this case you do need it. For the mass and heat transfer model, you can see that geometry is required for any type of application. The reason is that the correlations, you can imagine, they cannot really work without actually having knowledge of if we have a trade column, if we have a packed column, what type of packing we have, what is the geometry of a tray. So that's the reason why for mass and heat transfer model, you always have to put the full geometry in. So you might be asking yourself, why would we like to use the mass and heat transfer model if it actually requires some extra information? Here you can see kind of a summary of the advantages and disadvantages of the mass and heat transfer model. One huge advantage is that no empirical value is required for this model type. So when I mentioned efficiency or HETP, that's not something that's carved in stone. That's something that you might find in literature or might be well known from the industrial practice, but it's hardly a single value. It may vary. With mass and heat transfer model, you can get a fully predictive model where you don't have to worry about this empirical value. Another point we have here is related to agreement between reality and model. So we have incorporated the mass and heat transfer model into Promax in 2016, I think. It was actually before I started with BRNE. And from our experience, it really does a better job when it comes to matching plant data. Of course, we were as well kind of hesitant in using this novel model at first, but from what we've seen, it really is a better way to get closer to plant data when you're modeling an operating plant. Another thing is precision. So you can imagine if you're modeling a trait column with ideal stage model, you are going to have less stages than in reality. Also, when it comes to packed columns, the increment height is typically shorter than height equivalent to a theoretical plate. So you're going to end up, again, with better granularity. And that's the reason why you can better investigate temperature profiles, composition through the column, etc. And you're also getting more information about the mass transfer rates, about mass transfer coefficients. And so generally, you're going to get more information and better precision. And one thing I'm mentioning here, and that's also the motivation why we're even doing this webinar, is that it's extremely easy to use for packed columns. You will see this in a bit on a demonstration. Of course, each coin has two sides, so I cannot really say only the advantages. There are some disadvantages. One of them I've already mentioned, and that's that full geometry is always required. And the other disadvantage is that it's a bit more compute intensive. So you can imagine that since this model is more complex than the ideal stage model, it also takes a little longer to converge. All right, the part C, so packed columns using mass and heat transfer model, is something we will demonstrate in Promax together with the previous part. So we are going to basically do kind of a cross-section through all these topics in Promax, talking about trade columns and also talking about packed columns. So I'm going to switch to Promax, and we're going to basically run through a couple of flow sheets I have prepared, and each of the flow sheets represent a different case. So we are going to start with a little bit of intro, and then we will be using ideal stage model for a trait column, Masani transfer column model for a trait column, and then we'll move on to the packed columns. So let's start with this first question. Here we have a simple dew point control planned, and the column we will be modeling is this stabilizer. My question, if I tell you that this is a column model using ideal stage model, my question is this a trait column or is this a packed column? So most of the answers are saying trait, and I definitely agree with you that, you know, for this type of application, trait columns are definitely more popular. But on the other hand, model-wise, this could as well be a packed column. We don't really put in any information about geometry. We only using this model approach where we use some number of theoretical traits, and we can later translate these ideal stages to packing, just like to number of traits. So this is one of the advantages of the ideal stage model, that you can, if you are running on some feasibility study in a very early stage, you are able to create a model without even figuring out what internals you will need. So it is definitely, you know, a good thing about the ideal stage model. I'm going to show you how you can create a model like this. So if I switch to this next flow sheet, which is basically the same thing, but just unsolved, now we are going to use the knowledge that we learned in the presentation, and we are going to put in some specifications. Before we get started, as I said, it's more typical to have trait columns for this type of application. So we are going to model a trait column with 16 real traits. And since the efficiency, overall efficiency of a stabilizer in this kind of application is typically somewhere between 40 and 60%, I'm going to assume that it's 50%. So that's the reason why we saw 8 ideal stages on the last flow sheet. So now I would like you to kind of guide me through all that's necessary. So just throw the ideas at me and tell me what were the specifications I mentioned in the presentation that we have to make for the stabilizer. Definitely, we are going to have to make a specification because we have a reboiler, which gives us a degree of freedom. So we can check that if I open the stabilizer and go to specifications, you can see the specification is already created. And the way the reboiler is controlled here is that we have a specification for the read vapor pressure in our bottoms. And based on the specification, Promax is going to figure out how much reboiler duty is necessary to reach this. So that's one thing. We had 3 more things that we need to specify for every single column. Do you remember which were these? Full geometry is something that we could specify, but since we are using an ideal stage model, it's not going to affect the separation results. So we could put it in terms of hydraulics and their evaluation, but in terms of separation, this is not really necessary at this point. But we have some other answers like pressure profile, which is definitely a good answer. And so we can move on to pressure profile. You can find this under process data. If you go to stages, here you can specify pressure change. I also mentioned if you have the geometry specified, you are able to calculate pressures from hardware. But since we are kind of at the, you know, say beginning design phase and we want to keep it as simple as possible, we are just going to use our engineering judgment and say that our pressure change is 0.15 bar. All right, so that was pressure profile. If I switch to column, here is, you know, the first step I mentioned, and that's model type and ideal stage column type. And you can see what we're using here is actually the default, so we don't have to worry about it at all. But always make sure that, you know, on this page you have the appropriate model type you want to use. All right, so what is the last piece of puzzle I'm missing here. If I switch to connections and take a look at how many stages I'm currently using, the default in Promax is 2 stages. And I said that we have 16 real trays that we want to model and represent by this model. And we assume 50% efficiency. So just like we saw on the first flow sheet, we also have to bump up the number of stages to 8 ideal stages we want to use in this specific case. And once we do all this, even without any geometry, I'm just going to show this to you real quick. There's no geometry, and we are able to execute the column, and we are able to get results. What I'm going to do now is that I'm going to take this as kind of base case, and I'm going to model the same thing with the mass and heat transfer model. I'm just going to do a small change. I'm going to change or check what the current Reboiler Duty is. It's around 760 kilowatts. And instead of using the original specification of read vapor pressure, I'm going to switch it to calculation. Once I do this, you will notice that the number of degrees of freedom has increased to 1. And this allows me to specify the Reboiler Duty instead. So I'm going to basically have fixed Reboiler Duty and look or evaluate the separation performance based on the read vapor pressure in my bottoms. If I execute the flow sheet one more time, I can check the current read vapor pressure. I can also create a call out in order to report this. So read vapor pressure is something you can find out through an analysis. If I go to this liquids to pipeline stream and switch to analysis tab, you will see that there's a vapor pressure analysis created for me. And one of the parameters here is read vapor pressure, which if I switch it to PSI, should be identical to what we saw in the column. And as I said, I can report this with a callout. Callout, if you are not familiar with it, is basically a simple way to report some properties, some results of a process stream. And as you can see, you are able to take this tail of the callout and attach it to this connection point, this small gray dot on a stream. And once you do this, the two are kind of linked together. And that means that if I double click on the callout, I am able to go to analyses, to the vapor pressure analysis, and select read vapor pressure in PSI. I'm just going to deactivate some of the options that are not really necessary for me. And this is basically kind of the result of this first ideal stage case. I have prepared another flow sheet where we'll basically start from same case, and we are going to transfer this ideal stage model into the mass and heat transfer case. So what do I need to do? First of all, I'm going to use a different number of stages. In this case, each real tray will be represented by a model tray. And that means that if I'm thinking about 16 real trays, I need to use this exact same number for the number of stages. So I'm going to open the column, and under connections, I'm going to increase the number of stages to 16. I'm going to go to process data, and I will switch the model type to mass and heat transfer model. The pressure profile doesn't change. The specification is just like we left it. So we have calculation for the read vapor pressure, and we have hard-coded value for the Reboiler Duty. And with this information, if I try to execute the column, I will get an error. So Promax is going to kind of guide me that this is not enough information for the mass and heat transfer model, and I do need to put in some column hardware data. To specify this, I need to go to this hardware section, and the first subsection we will be looking at is general. And here I I need to put in some information in order for the column to work. We either can specify diameter or fraction flooding. The way it works, if you specify diameter, this is going to be calculated, and the other way around. Since I don't really have a good sense of what would be an appropriate diameter in this case, I'm going to just specify that we want to target 70% fraction flooding. As soon as I do this, you will see the diameter cell is grayed out, so I can no longer specify it. Another column we will look at is system factor. This is basically a factor that accounts for foaming in a column. If you have an ideal case where there's no foaming at all, you can use 1, but in reality, you need to derate the column for foaming, and for stabilizer, I would say that fairly typical number is 0.9. What I can do now is to select these two cells while holding Control, which will select them both. And then I can use copy to bottom button here, which will basically populate the value from the first row into all the remaining rows as well. So this was setting the general hardware. You can see we have selection of trays as hardware here, and that means that we probably need to take a look into another subsection, which is tray. If I go to tray, here we have a lot of default values. If you are not familiar with these different font colors we have in Promax, the way I can tell that these values are default is that they are black. If I go back to general, you will see once I specify something as a user, it's going to be blue. So the two cells I'm missing here, or columns I'm missing here, is tray spacing and wear height. So I'm just going to use some parameters that are quite common for pretty much any tray column. So I'm going to use 0.6 meters tray spacing and 5 centimeter wear height. And this is pretty much all I need to put in. Note that the other parameters we have here, such as fraction active area, such as number of passes, this is something that if it's different for your column than it is in the model, make sure to tweak these. Even though the default values might be appropriate for you in a lot of cases, if they're not, make sure that you adjust them. All right, so this is the kind of minimum amount of information we need to provide in terms of geometry if we're solving a tray column. And now I can go back to my flow sheet and I can execute it. One thing you will already notice that it takes a little longer for the column to turn green. So there's a little more numbers running here in the message log, and that really just shows the complexity of the model, and there's a reason why it takes slightly longer to converge. All right, so let's take a look at the read vapor pressure right now. It is lower than in the ideal stage model case. So what does it say about my assumed efficiency? I assumed efficiency of 50%. Is the real efficiency, is it higher or lower? This is a bit of a tricky question. It's kind of, you tend to say lower because we have lower read vapor pressure here, but actually we're kind of over treating here. We are able to run more of the light ends out of the liquids than is necessary or than what we saw in the previous case. So actually the efficiency in this case is very likely higher than what we assumed with the ideal stage model. So I said that the range typically somewhere between 40 and 60%. So what if we say that the efficiency was 60%? With 60%, the number of real trays we would need for this kind of application would be 13, more or less. So if I go back to the column and go to connections and adjust the number of stages to 13 and execute the flow sheet, this might probably help get closer to the ideal stage model. And if I compare the results now, you will see that they are almost identical. One thing it tells you is that you are able to get almost identical results for ideal stage model and mass and heat transfer model. The difference is that with mass and heat transfer model, you can directly evaluate the number of real trays you would need for this kind of application, while for the ideal stage model, you have to make the assumption. And in this case, I actually made a bad assumption. I was too conservative, and I actually used 50% when in reality I would probably end up with a slightly over-designed column. In this case, it wasn't we saw that the sensitivity of the process wasn't too huge. So in this case, it wouldn't be a big deal. You always want to have some safety margin. But a typical application where we see that the disparity between the operating plans and the assumption in engineering is, for instance, sour water strippers, because the range for sour water strippers you would find in literature is somewhere between 33 and 50%. First of all, this is quite a wide range, right? And second of all, I completely understand that engineering companies in most of the cases would rather stay on the safe side of things and decide to go closer to 33%. However, our experienced from matching the plan data using the ideal stage model is that in most of the cases, it's actually closer to 50, sometimes even exceeding 50. And so the mass and heat transfer model for trait columns, as we see here, can help you get a more competitive design when it comes to engineering work as well. And for the operating data, for matching real facilities, it is even simpler. So this is just kind of to show you why it might be a good idea for you to use mass and heat transfer model, regardless if you are in engineering or if you are in operation. All right, so I would like to also take a look at the result more closely. So I'm going to go to the stabilizer column, go to process data, and start at the top with the properties and column. So you can see, or you could see, that with mass and heat transfer model, we have slightly more options here on this first page. In most of the cases, you don't have to change any of these. Just so you know, for instance, this interfacial area factor is something you can use as a tuning factor when matching plan data. It is very rare for this to change. If you are kind of thinking or considering using this, you might also reach out to us and see if we have kind of second ideas or different ideas on how to match plan data, because very often there might be some other ways to get a better agreement between model and reality. If I switch to mass transfer here, there are a few things I would like to point out. Regarding the correlations for the mass transfer and for the interfacial area estimate, I definitely wouldn't change these for trait columns. So the AICHE, the American Institute of Chemical Engineering correlation we're using for the trait columns is definitely the best one, and the same applies for the interfacial area. The mixing model, this is something you might occasionally want to change. With well-mixed model, we basically assume that on a given tray, we have uniform composition in vapor phase and uniform composition in liquid phase. So the composition is constant on this tray. Sometimes, if you have, for instance, a large diameter trait column where you can imagine that there's some composition gradient across the tray, you might want to use liquid plug flow. In that case, we are going to have some approximation of continuous gradient among this increment, among this tray. The same applies for the vapor plug flow. This is something you might want to use if there's a lot going on in terms of mass transfer on a given tray. If you have a really steep temperature change between the two trays, you might want to consider vapor plug flow. But I would say that in 95-99% of cases, well mixed is the best option. So I would change this only on the rare occasions, and again, you can double check with us always if we think it's a good idea. One last model we have here is equilibrium stage, and this is basically just shifting the mass and heat transfer stage into an ideal stage. So just so you know what this equilibrium stage means. If I go to mass transfer multipliers, this is even more complex way to tune or data fit for data fitting. Again, something you probably are not going to use, but I want to kind of give you the full picture of all the capabilities and options you have available. All right, for the hardware, we looked at this already, but I also wanted to show you what we have here under results. If you go to mass transfer, you will see that unlike for the ideal stage model, you are able to see mass transfer rates on each tray individually for the components. And you are also able to see the mass transfer coefficients and the Marfori efficiency. So it really gives you a huge data set of information and something you can investigate if you are interested. What's also good to look at is this plot step. If I switch here, you are able to see the temperature profile, or you are able to see how the different components change in terms of composition in vapor and liquid. Here we have it for vapor, but you are also able to activate it for liquid. And as I mentioned, if there is some tray where you see like super steep curve, then for instance, the vapor plug flow option might be good. But in most of the cases, the well mixed, first of all, it is the most conservative option. And second of all, I haven't really seen using it too often. So this is just something to note. One last thing I would like to point out here is that you can see that we have separate curves for vapor and liquid. This really just shows that we have non-equilibrium model, and that with ideal stage, we would have just one curve. With the mass and heat transfer model, you are able to investigate vapor and liquid temperatures separately, which might be useful, for instance, if you are concerned about metallurgy of your column and exceeding the absolute temperature limit. This is definitely going to give you more information about it. So this was the part where we were focusing on the trait columns. And now I think it's great time for your questions regarding this part. So another question and answer window where you can ask whatever you want. We already have one question, and that is whether or not the heat and mass transfer model takes viscosity and surface tension into account. Yes, it does, absolutely. The physical properties are accounted for, which is why it's really powerful in terms of being predictive. So yes, the answer is absolutely. Antonio is asking if we have any guideline to select a good mass transfer correlation. For this specific case, so for trait columns, I would definitely recommend to use the default correlation, the AICHE. For the random packing and structured packing, sometimes you might want to change to something different. I will discuss this in a bit, but yeah, for trait columns, so for what we've discussed so far, just use the default one. Jonas is asking, how can I determine the number of stages needed? Probably the best way to investigate this is to use scenario tool, which is a tool we have in Promax, which allows you to run parametric studies over a range of the stages. So you basically can, report or have as your outputs some key performance indicators, and your input will be the number of stages. And based on that, you can see, where is kind of your sweet spot and where you have good safety margin, and at the same time, you don't go too far with, kind of diminishing returns. Regarding liquid columns, that's a great question. So far, we don't have correlations And as far as I know, there are not really too many correlations even available in literature for liquid-liquid columns. So when we are talking about liquid-liquid columns, we are still limited to the ideal stage model, but you are able to model liquid-liquid towers, absolutely. So let's take a look at packed columns. We said that for packed columns, if we are using an ideal stage model, what we would use is the concept of height equivalent to a theoretical plate. The question is, what is an appropriate HETP for a given application? So what I can try is to take a look in Promax Help, because Promax Help, we really have a lot of useful information in here. So I'm hopeful that it can also tell me something about HETP. When I search for HETP, you can see we have a page about height equivalent to a theoretical plate, and we can take a look at this to kind of see what it takes to use this concept. So we have kind of a list of all that affects the HETP. So it of course depends on packing type and size. It depends on gas and liquid traffic. It depends on some packing supplements we might have, such as distributors, etc. It depends on system pressure. If we have ionic system, such as in sweetening, it's also going to make a difference. It depends on physical properties. So a lot of basically factors we need to take into account. A quick answer for Celine. She was asking about how can I bring up this page. If you want to access Promax Help, you simply need to click on this question mark here in the Promax ribbon. So this kind of gives you an idea that it's not really simple to come up with a good value for HETP. The other page we can, for instance, take a look at specifically for the stabilizer application is this typical fractionation parameters, which is another page we have here. So here for packed columns, you can see, and this is actually kind of interesting, for pole rings 1.5 inches, the height equivalent to a theoretical plate can be anywhere between 2 feet and 3.2 feet. Depending on the pressure and what type of column it is. So this is a really wide range, right? So we would probably need something a bit more sophisticated. If I go even, or if I scroll even down here, you can see there are some rules of thumb. We are able to come up with HETP based on viscosity and surface tension, but there are some limitations, and there is a recommendation to add some safety factor. So generally, it's not really easy to come up with this value. What you always can do is to reach out to a vendor, and he will probably give you a trustworthy value for HETP, maybe even over some range of, I don't know, F factor or something like that. But what if you have or want to investigate different feeds? What if you want to investigate multiple packing types? What if you want to change the operating conditions significantly? What if you want to operate at different pressures and temperatures? That's of course going to affect the physical properties as well. So there's a lot of things that can affect HETP, and it's really hard to come up with some value. That's the reason why for packed columns, basically for 99.9% cases, we recommend to use the mass and heat transfer model. In that case, you don't have to worry about any of this. You simply, put in your packing type, how tall the packing is, and the specifications we also did for the other columns, and that's it. So it's really simple. I'm going to demonstrate this to you in the next flow sheet. So I'm going to switch to packed columns. And for this demonstration, I'm actually going to use an amine sweetening unit. So we have 2 columns we will be use this approach for, and there's this main absorber and this small flash absorber which sits on the top of flash drum. First part, I'm simply going to show you, how easy it is to set up. The second part, we will get into a bit more detail, and I'm going to explain you some of the decisions I made during this specification. Here we have what we want to put in. So we have this main absorber with a diameter of 0.7 meters. It's 8 meters of packing, and we're using Rashik super rings here. One thing we have to decide is the number of calculation increments. What we recommend is somewhere between 0.3 and 0.6 meters. Just to make it easier for me to do the math, I'm going to use 0.5 meters. So for 8 meters of packing, I'm going to use 16 calculational increments. Now I need to go to process data. And the model type we're going to use is mass and heat transfer model. You might remember that for amine screening applications, we need to switch on the kinetic model, and that's the reason why I need to switch the column type to T-suite absorber/stripper. We also have to specify the pressure profile, so we can put it 0.3, for instance. This is my guesstimate. And now I'm going to go to channel hardware and specify that we have 0.7 meters diameter. System factor might be something like 0.85 for an amine absorber. And I'll go to random. One step I missed was switching to random here on the channel page. And now I'm going to go to random. And as you can see, we have a very comprehensive list of packing types in Promax. You are also able to put a custom packing here. So with this user-defined random packing, you basically are able to put in also something that you would be missing in here. But the Rashik super rings is something we have here. So I'm going to select this 1-inch metal super rings. And one last thing I'm missing is the depth of packing, which is 8 meters. So under total height, I'm going to specify 8 meters. And what I can do now is simply execute a column. So as simple as that, I just, put in the number of increments, do all the specifications, which I also need to do for ideal state model. And then I just say what type of packing I have, what is the diameter, and that's it. June is asking me, why did I select 16 stages? I might have go too fast through this section, but I basically said that the recommendation for the increment height from Brian Research and Engineering, based on, again, testing it against plan data, is somewhere between 0.3 and 0.6 meters. We will get more into the increment height in a bit, so bear with me for a moment, June. I'm going to explain this. I would say it's pretty simple, definitely, simpler than trying to figure out what is an appropriate HTTP for my application. So a few things, again, I would like to discuss here that are different from trade columns is if I go to mass transfer, just like before, here actually I would recommend to change the mass transfer correlation to billet-Schultes. As default, we have Onda for random packing. And this type of packing, the reason why we're using it as default is that it is applicable to any type of packing, because the billet-Schultes correlation, it requires billet parameters, and you can check if a given packing type has these parameters available or not by going back to random. And if you go to the right, here you will see these 4 columns with the billet parameters. If these are missing, that means that the given packing type is not suitable for the billet-Schultes correlation. And that's the point where you would need to use something else than billet-Schultes. But for most of the cases, I would recommend switching to billet-Schultes. For structured mass transfer correlation, billet Schultes is the default. So again, in this case, I would recommend using the default. We are not going to discuss structured packing during this webinar, but it's basically no different from what we are covering right now. That was this first absorber. Now we're going to do the same thing for the second absorber. You can see this one is way shorter, way smaller in terms of diameter. But I'm going to use the same recommendation for the increment height as before. So we have 1.5 meters. So that means if we're using 0.5 meters increment height, we have 3 stages. And I'm going to go to process data, again, mass and heat transfer model, switching on the kinetics by selecting T-suite absorber / stripper, putting on pressure change, which in this case is probably lower than before. So I can say maybe somewhere around 0.1. And now I'll go to general, specify that it's 0.2 meters in diameter, the same system factor as before. I'm going to switch the hardware type to random, and I'm going to select hole rings 15 millimeters from the selection. And last but not least, the packing depth, which is 1.5 meters. I'm also going to change the mass transfer correlation. And that's it. So just to kind of demonstrate to you that it's really simple in this first, say, initial specification to put your packing in Promax and get results. One thing you might be curious about is why are we using the increment height of between 0.3 and 0.6 meters? Because maybe from your university you might remember if we were talking about numerical methods and kind of deciding how big or small some increments should be if you do something like numerical integration. One idea might be that the shorter the better. The more increments we have, the more accurate results we're getting. I'm going to explain this to you, why we should target somewhere between 0.3 and 0.6 meters. If I use this very sophisticated drawing or graphic program, which is Microsoft Paint, and I draw a column here. So, let's say that it's an amine absorber and we have basically our sour feed entering the column at the bottom. And then we have our sweet gas leaving the column at the top. We have lean amine entering the column here at the top, and the rich amine is leaving at the bottom. So you might remember when I was describing the mixing model that we assume well-mixed mixture in a given increment. That means uniform composition in a given increment. So if we decide to have a lot of short increments in our column, if we decide to use, I don't know, 10, 100, a lot of increments, what it means in terms of concentration is that we end up with a perfect countercurrent case. In other words, it would correspond to a case where the sour gas is basically going straight to the top while the amine stream would be contacting the sour feed in countercurrent. So we would probably end up with something like this. But this is not really a good approximation of reality. The reason is that in reality, you are very likely to have something like eddies on your vapor stream, or you might have some liquid being splashed up, kind of entrained by the vapor. So there's going to be some extent of bag mixing in the column, and that's the reason why, in order to account for this bag mixing, we want to take some step back from the pure countercurrent flow, and we want to use slightly larger increments. So that's how we came up with the recommendation between 0.3 and 0.6 meters. And again, it is something that we have carefully tested or benchmarked against plan data in order to be sure that that's typically the best value to use. One thing that might be kind of abstract for you and hard for you in terms of evaluation is how much safety margin I actually have within this recommendation. Generally, if you are using a value closer to 0.3, that means that you are less conservative. If you want to be more conservative, you would use taller increments, so you would be closer to 0.6 meters. And you actually also can kind of touch the safety margin yourself. You can investigate it yourself. So in the last part, I'm going to show you some sensitivity analysis that I ran on the specific case that I demonstrated the packing approach in the first place. And I'm going to show you how you can do three things. First of all, you can quantify safety margin that we already have built in this recommendation, because there already is some conservatism in this recommendation. Second of all, I'm going to show you how you can come up with even less conservative design if you want to. And the third thing, I'm going to demonstrate you that the optimal increment height might depend on the column diameter. All right, so that's what I have this last flow sheet for. This is linked to an embedded Excel worksheet I have here. So I have two sheets here. One of them is for the main absorber, and the second one is for flash absorber. And what I was doing here, I was increasing the number of stages. So this is something that you might also do, Jonas, when for the trade columns. In this case, we are controlling the number of increments, but the idea is the same. And I'm reporting the increment height, and I'm reporting what's important for me in terms of performance. So I'm reporting the H2S and CO2 concentration in my sweet gas. And these concentration, they can show me when I'm approaching the countercurrent case, the countercurrent behavior. And what our developers find out is that the good approach to account for bag mixing is to basically find out where you are getting to this limiting value and take some step back from the limiting value, typically somewhere between 10 to 20% when talking about the number of increments. So let's take a look at this main absorber. You can see at first, as we are increasing the number of increments, the H2S concentration in sweet gas is dropping quite a bit. But then it really flattens. The curve is becoming very insensitive to the number of increments. And so we might take a look at where we think, and of course this is somewhat subjective, where we think we're approaching the optimal counter current flow. So how many stages would you say is probably close to counter current flow, where it starts to level off? Let's say somewhere between 40 and 60. If we take a look at these values, probably this 56 or maybe 48. It's already, in this case, it's already kind of flat. And Erica has an interesting point that she would select around 100 to be on the safe side. I understand where you're going with this, but the way it works is actually the opposite. So if you want to stay on the safe side, it is better to select a lower number of increments, so the higher number or the taller increment height. To kind of stay on the safe side, as you suggest, probably using, instead of 56, maybe using 48 is something I would recommend. So I'm just going to, say that 48 is what I consider as the limiting point where we're approaching the countercurrent behavior, the countercurrent flow. And based on this, I'm going to take, as I said, or decrease, I'm going to decrease the number of increments by 10 to 20%. So, 80% case and 90% case. And I can basically take this 48 and I'm going to multiply it with this. And then I can translate this into increment height by taking 8 meters and dividing it by the number of increments. So what you can see is that we would probably be already kind of safe using 40 increments. So increment height of around 0.2 meters. So this really shows you that with the typical recommendation we give between 0.3 and 0.6, you already have some built-in safety margin. And if you are still kind of suspicious that you might want to have some additional safety margin, or you want to evaluate the safety margin yourself, this is something what you can do. You can basically test the sensitivity of the system over a range of the number of stages, and you can run up to really high number of increments to make sure that you really get close to the countercurrent behavior. And then you can take some step back to account for the back mixing, and you might, as you can see, probably end up with an increment height which is even smaller than our recommendation. All right, so this was the main absorber. Now let's do the same thing for the flash absorber. So I'm going to switch to the next sheet, and we're again going to take a look at where we think are approaching the countercurrent behavior. So if we take a look at the plot, I'd say probably around 30 stages looks quite good. That's the point where it levels off. So I'm going to do the same thing. Say 30 is the point where I'm getting really close to it. And then I'm going to take a step back. I'm just going to adjust the packing height to 1.5 meters to get these values right. And you will see the increment height that we obtain when using the same procedure. However, for a significantly smaller diameter, is actually something like half of the previous value. So this is just to demonstrate that if you have a really small column, something like this flash absorber on the flash tank, you might use even shorter increment height than the recommendation. So, for instance, just my experience, if I'm modeling a flash absorber, I typically use as an initial value, I typically use 0.2 meters. And this should be, a good starting point where when matching the plan data. Of course, for plan data, it's something that you can use as a tuning factor. But even for design, you should definitely be on the safe side in most of the cases. So Tanya was asking if I have to use any part of HETP depending on each type of packing. No, absolutely. This mass and heat transfer model is completely independent of the whole concept of HETP. So the increment height, I think that's something we kind of covered as it went. But the increment height is completely different concept from HETP, and it has nothing to do with it. So you don't have to really worry about the HETP approach when using the mass and heat transfer model for packed columns. So another question from Erica was checking the specification and against increment height. Could you maybe expand that question a bit, Erica? In the meantime, I'm going to answer the question of Christian, who's asking if I can repeat why a lower number of stages is safer. So if I go back to this a bit ugly drawing of myself, you will see that the lower number of stages means taller increments. And generally, if you have taller increments, that means that we assume more bag mixing, more deviation from the pure counter-current flow behavior. So that's the reason why it's safer to use less increments and taller increment height. Tanya is asking what I said is a typical increment height for amine absorber. This is in line with the recommendation, with the general recommendation. So I would say between 0.3 and 0.6. Again, if you want to be more conservative, you would stay on the higher values, so closer to 0.6. If you want to be less conservative, you can go around 0.3. Or if you want to do this little study I just showed you yourself, and maybe be even less conservative, you definitely can use scenario tool and random parametric study to see it yourself. Antonio is asking, how do I relate the increments to height equivalent to a transfer unit, I believe it is. This is again completely independent of this concept. So you don't have to really worry about, or it is not related to HTU. Christian has a really good question. For design, as you normally don't have geometry specifications, how is possible to use this mass and heat transfer approach? So as I suggested, the ideal stage model still has its role in the practice of a process engineer. So if you are in a very early stage of process design and you don't have decided about the geometry yet, you might want to use the ideal stage model just for the initial mass and heat balance. But when it comes to a little more detailed design, to really get trustworthy results and to not worry about HETP, our recommendation definitely is the mass and heat transfer model. So just to clarify one more time, the number of theoretical stages and the number of increments in the mass and heat transfer model, these are two completely separate things. So they are not related in any way. All right, so just to kind of wrap this presentation up, a quick or a few conclusions we have here. So you could see that we basically have two model approaches here, the ideal stage model and mass and heat transfer model. Based on our experience over the course of the last few years, we recommend the mass and heat transfer model, and we consider it a new gold standard thanks to the accuracy and the level of complexity. One really important thing to mention is that if you have any questions, if you need any assistance related to columns or anything else in Promax, please do not hesitate to reach out to us. That's what we're here for, and we'd be happy to help you. So if you have a system you are not sure Mazzini transfer model is applicable for, or you are not sure what increment height you should select, you can always give me a call, email me. If you are wondering where you can reach out to me, here you can see my email address and my phone number. Or you can just send an email to our general support, which is support@bre.com. I would like to thank you for your attention. Thank you for being here with me today. I hope you enjoyed it as much as I did, and I really hope to see you at some of the future courses as well.